So we'll put a picture of a visual. So we'll put up a picture of a visualization. So we'll put the diagram or the models, the picture. I will put. Hi and welcome to GeoCave, or welcome back if you're a returning viewer. My name is Asha. I'm a geologist living my life in Norway, and I talk about anything geology related. Today we're going to have a lot of fun with some geophysics, so jump on, fellow cavers. Yeah, so it's been a while. Last time I made a video, it was before Christmas, around November, and I thought I would take a break in November and then I would come back after Christmas, after the New Year's. But I always seem to have problems starting up the year. It always ends up being at least March before a new video comes. So, but now I have actually filmed a little video for you. So the last time it was an article by what's the guy? It's not Tardino. It's Hale. Yeah, Hale from 1987. 87, I think it was 1987. And it was about how he theorized that paleointensity could be used to tell, like paleointensity could be used to say something about the nucleation of the inner core. And we will continue with that today. So, but with a different article and a different view. So yeah, I think it would be quite good. So a funny thing about me is that you probably don't know, I did take a lot of physics and math when I took my bachelor's degree, but I was never like a student who got top grades. But it was first when I started my master's degree in geophysics that I kind of like understood physics. Like before I would be like, I would do the math and do the physics, but I had problems kind of like visualizing it or like getting the hang of it. But when it was connected, when physics was connected to geophysics, I started to get the hang of it. I understood the math and the physics much better. So yeah, I don't know if you watched the Big Bang Theory, you know, when Sheldon is kind of like they're fighting some kind of, what is it called, like ping pong game, and Sheldon goes out and like says, geology is not a science, true science, or something like this.
Geology isn't a real science!
I really feel that it's not true. Like you know, all natural sciences is called natural sciences because, you know, it's based in what we see in nature. So it's actually quite a stupid quotation. Geology is so much fun. Yeah. But yeah, so today we are looking at this article by a guy named Aubert. I have made an intro for the video, so maybe we will jump to that. Yeah, so. It's a complex job describing the evolution of the geodynamo. But that is what Aubert and his team are presenting here. They use physics from Magnetohydrodynamics to do so. The article is called Modeling the Paleoevolution of Geodynamo. And they are presenting a new view on the discussion of the age of the inner core. You know, old rocks is not always a good source of paleomagnetic data due to weathering, erosion, and sometimes metamorphism. So this study is supposed to kind of like support the data we have and see what kind of like what makes sense and what doesn't make sense in a way. They simulated how the Earth's liquid outer core moves and generates the planet's magnetic field using physics equation. So first, let's paint a picture.
Hey, another jellyfish!
It's Squidward, silly!
Aubert describes the model as, and I quote here, an electric conducting incompressible fluid in a gravitational spherical shell between the radios R1 and R0. The shell is rotating about an axis z with an angular velocity and convecting thermally and chemically. So this is the visual kind of like, or the geometry of the model. Then this model is described in 5 different equations, or well, actually it's actually 6 equations. And the first thing they present is a formula for. So I thought we would just zoom in on the different equations here, so it's easier to follow. The first equation we're presenting is the codensity equation, where codensity is a variable that describes fluid flow in the mantle boundary by combining temperature convection and chemical convection. And convection is kind of like a way to move heat. C is codensity here. The first part is describing the rise and fall of fluids dependent on temperature. You can see the T, temperature is T. And the last part is almost giving the direction of the fluid. You can see with the delta and the density. So that's quite cool. Then we have the Navier-Stokes equation, also called the fluid momentum equation. And it's a way of describing motion of fluid. And you can see here the codensity is incorporated in the last part of the equation. And there's a lot of letters here, some of them in bold. And when they're in bold, it means that they are vectors. I will come back to that later. And the triangle pointing downwards, that's a way of calculating with vectors. So but the first part is describing, like before, the equal sign is describing the incompressible velocity field, which you can see as the letter U. The first part is respect to time, and then further you have its angle in space under the influence of pressure. You can see here P is pressure. So, and the second part describes movement of fluid, this using Rayleigh number, which is represented with RA. And but let's stop the bus here. The Rayleigh's number is a dimensionless number in fluid dynamics that predicts when heat transfer in fluid will switch from conducting to convection. So it's like either moving like through the material or with kind of like. So, okay, we go back to the Navier-Stokes equation here. And the last part of the equation is where the Rayleigh's number is set in relation to the dimensions of an orb. And this is put together with the magnetic field evolution. You can see it with the big letter B. So, so that's kind of like the Navier-Stokes equation. So then we have the magnetic induction equation, and the magnetic induction equation describes how the magnetic field evolved. You can see here the magnetic field is set in relation to time, the first part, and then it's describing the magnetic field as a vector. And what is a vector? Vector is actually just a way of describing values for something in time and space. For example, if you have like a dot on the screen and you want it to move in time, you can like mathematically put it into a matrix, like a matrix, and you will then have the coordinates for the dot, like x and y, and then you can have the values for time as a separate part of the matrix. So and this in combination with the velocity field, there are two parameters here which is describing the magnetic field. E here is rotation versus viscosity, and PM is viscosity versus magnetic diffusion. Yeah, so but that is actually the magnetic induction equation. And then we have the scalar transport equation, and you can see here codensity is repeated, and it is an equation that describes codensity related to time. Yeah, I'm not going to say much more about this one. Last but not least, we have the boundary conditions, and boundary condition is almost like when you set rules for a game. You kind of like set criteria for how the game is going to be played, and these two says that the fluid is the first one says that the fluid is incompressible, and the second one says that magnetic monopoles doesn't exist, which they don't. So it's like and fluid is incompressible, so it's just like stating it in mathematics, kind of like, or physics. Yeah, I don't know if this makes sense, but it gives you a kind of like a short introduction to magnetohydrodynamics. I don't know, it's quite heavy actually, but yeah, but you get a feeling of what the researchers are using as their foundation for the results they get. So yeah. So with this in mind, let's see what the Aubert's model did. The first thing they did was make a numerical dynamo model, one with the focus on chemical convection and the other one on secular cooling. Chemical convection being fluid movement governed by chemical composition, and secular cooling being slow, continuous decrease in Earth's internal temperature. So what are they trying to argue with these two models? Secular cooling is a model representing an Earth where the inner core has already been nucleated, so there's just heat leaving the core, while chemical convection is a model representing an Earth where the inner core is growing. So we'll put a visual up of the model here. So what we see is when there's almost no inner core, the liquid outer core flows in a very simple, symmetric way. This simple flow makes the magnetic field strong in one pole and weak in another. In the models where the dynamo is driven only by cooling or secular cooling, the inner core does not take part in the convection. Because of that, the changing of the inner core's size makes almost no difference to the magnetic field. The usual link between the inner core size and where there is reversed magnetic patches appears does not work. So the chemical convection model is much more relevant, and the most interesting part comes now, because the driving force for chemical convection is temperature. Modeling ancient heat flow might give us some indication of timing of the nucleation of the inner core. And heat flow is another part of geophysics. I will not go into details on this in this video.
Are you sure?
But it is, as it says, movement of heat. And that is what they did. They combined this with a numerical modeling and modeled the heat flow from core mantle boundary. Again, they came up with two end members. One high power scenario where the heat flow was estimated to 11 terawatt, and one low power scenario with 3 terawatt. And these end members tells us something about how much heat is exchanged in the core. So let's look at one of the diagrams. On the x-axis we have time, and on the y-axis we have heat flow or power. So what are we seeing? In the low power diagram, the blue and red curve makes a jump around 1.8 billion years ago and symbolizes the nucleation of the inner core. The same thing happens in the high power model, but much later, around 800 to 700 million years. But the gray area representing the limit of power for nucleation of the inner core, and in the low power you can see that the heat flow between core mantle boundary, the black line, goes under this limit just before nucleation. Therefore, high power is argumented to be the most plausible scenario. So what can we take out of this article? First, the first part shows that even with a small to non-existing core, the early Earth would produce some kind of magnetic field, and it could even reverse. Secondly, with a high power scenario, the Earth's inner core seems to have formed much later than earlier thought. This disregards the two articles we have looked on earlier. They of course conclude with saying that more investigation is needed. As far as I know, in the field of paleomagnetism, Hale's article from 1987 hasn't been obsolete yet, and I'm scouting for new research. But physics never lie, and I find it kind of romantic that the formation of the inner core happened around the Cambrian explosion. But the future or the past will tell. So that's it for this time. Thank you for watching and have a rocky day.